Chapter 16, Lecture 1. This chapter will be over acids and bases, and we will especially look at acids and bases through the eyes of equilibrium, because to really understand the nature of these substances in chemistry, you have to understand equilibrium. So this will be the discussion of this in the subsequent chapter. Quick definition to recall what acids and bases are. There are two historical definitions that are usually given. The first one that's discussed is the Arrhenius acid and base, because this is the first time that acids were defined historically by a scientist by the name of Arrhenius. So an acid was defined as something that dissolved in water will increase hydrogen ion concentrations. And recall that hydrogen ion concentrations are can be expressed like this. So it is a measure of how much H plus there is in a solution, and if a substance increases that, then it's called an acid. By contrast, a base increases hydroxide ion concentrations, OH minus. And historically, these two substances were found to be extremely important in many chemicals, and especially the role in regulating reactions. So really, if you think about this, these two substances combined together give you H2O. So this whole concept of acids and bases really centers around water, because water, you can say, is part hydrogen ion and part hydroxide ion. In fact, when the two combine with an acid-base reaction, you get precisely water. So really, that's what an acid and a base can be thought of as referring to. Later on, the definition was modified slightly because the original definition only held for aqueous solutions. You had to be in water in order for an acid to really be called an acid. But it turns out that's not the case. There are many substances, notably bases, that can actually act outside of water and still do the same thing, still produce OH minus, for example. So, or I'm sorry, not produce OH minus, but still act as a base. So we've redefined our concept of acids and bases slightly, and now an acid is said to be a proton donor. Now recall, a proton is the same thing as an H+, so really we're referring still to the same species, a hydrogen ion, because a hydrogen ion from the periodic table, if you take a look at hydrogen, all it has is its mass is 1.01 roughly, which means it has no neutrons in its nucleus. If you remove its electron, you're left with simply a proton, and that's why this is called a proton. So an acid, by this definition, must have a removable proton. It must have a hydrogen on it. A base, by definition, is a proton acceptor, any substance that would accept an H+. And here it says it must have a pair of non-bonding electrons, and really that's the site at which the proton is accepted. The famous example of this is NH3. NH3 is the famous base, and if you draw the Lewis structure of NH3, what you'll see is that it has a pair of non-bonding electrons, and that's the site at which a hydrogen ion can bond, you could say. And many substances can be what we call amphiprotic. They can be both acids and bases, and here is where you see water. Water can actually act as both an acid and a base. Other famous examples, which we'll discuss and see, are this is the bicarbonate ion and hydrogen sulfate. So let's kind of visually see what happens anytime we have an acid dissolved in water. So most of these will circle around the discussions in water, most of these definitions of acids and bases. So because we said an acid donates a proton, the water then accepts that proton. So the H plus goes from, in this case, if you see, here's our hydrochloric acid, the H gets donated and the water accepts the H. Water, also recall, has structure, Lewis structure, that gives it unbonded pairs of electrons. So at this site, a hydrogen ion can bond. What you have at the end of this reaction is this substance. This is called a hydronium ion, And then this Cl minus that's left after the H plus was given off, we'll call a conjugate base. And the reason we're going to do this is because we consider now reactions to be equilibrium systems, and only through the eyes of equilibrium can we understand this substance as being a conjugate base. So here is a good overview of what this means. Every acid, here we have an acid, HNO2. Every time an acid gives up a proton, gives up an H+, in this case it gives it up to water, what happens is the conjugate base is formed. And because we now consider this to be an equilibrium system, we can think about this substance here, NO2, as being a base. And as it goes the other way, you can kind of see it accepting an H+ now from H3O+. So if you think about the reaction going backwards, NO2 minus goes to HNO2, which means it accepts a proton. So that's why we call it a conjugate base, because going the other way, it acts as a base. Likewise, water, which in this case acts as a base going forward, becomes a conjugate acid. And this conjugate acid can now give up a proton. If you go back over to the left side, you can see that H3O plus becomes essentially H2O again. So it gave up the H+, and it gave up the H+ to the conjugate base. So through the eyes of equilibrium, we can now consider your product to also be an acid or a base. And this step is very important in order to understand the further reactions of acids and bases. So why don't we do a little example. So here we're asking what is the conjugate base of each of the following acids. So we're considering all of these to be acids. And if it's an acid, recall that it will donate a proton. An H+ will be donated. So when HClO4, which is perchloric acid, gives up its H+, it becomes ClO4 with a -1 charge, because every time you lose a proton, you get rid of a positive charge and go down to negative. H2S likewise gives up an H+ and becomes HS- for the same exact reason. If pH 4 gives up an H+, then we go down to pH 3, and that's the conjugate base. And if HCO3 gives up an H+, it goes down to CO3 2-. So in all four of these cases, an H+ was donated, and what resulted was the conjugate base. Now these guys then are conjugate bases because they can now accept an H+ if you reverse the reaction, and that's what we mean by a conjugate base. And to fully show what's happening here, the part B says go ahead and write an equation which shows SO4 2- acting as a base in water. And then we want to identify our conjugate acid and base pairs. So SO4, the sulfate anion, will be reacting with water in an equilibrium system. So because we're told that HSO4 is a base, we know that bases will accept protons, which means there'll be a proton that comes from water to SO4, and as it accepts it, it becomes HSO4 -1. Notice the chart changed because we added a positive. And what's left over, we lost from water an H+, and we've got ourselves OH- left over. So this would be the reaction completed. Because we said that SO4 is a base, H2O must be an acid. H2O gave up the proton, that's the definition of an acid. SO4 accepted that proton, definition of a base. Then on the other side, your HSO4 became a conjugate acid. The reason it became a conjugate acid is if you think about the reaction now going backwards, going this way, HSO4 is seen as giving up its H. Notice it loses its H here. So that's why we call it an acid. And then likewise OH- is called a conjugate base. Conjugate base for the same reason, going back the other way, it accepts a proton. And your base on the left side will always be teamed up with your conjugate acid on the right, and your acid on the left will be teamed up with your conjugate base. So these are chemically connected, and they differ, these conjugate pairs differ by just one H+, one proton. Let's talk a little bit about the strength of acids and bases, and in general, we'll say that the stronger the acid, the weaker its conjugate base. So we talked about this earlier, but strong acids, by definition, completely dissociate in water. What that means is if you have, say, HCl in water, it completely dissociates into H+ and Cl-. And through the eyes of equilibrium now, if we think of this as an equilibrium system, then most of the equilibrium lies, you can say, on the product side, and there's really almost nothing on the reactant side. So the product, these substances right here, are very weak. Cl is very weak as a base, is the idea. If we begin with a weak acid, then the conjugate bases are weak bases, because going the other way, the equilibrium system allows these now conjugates to react as bases. And then substances with negligible acidity, which means a substance that's barely acidic, will actually have strong conjugate bases. So again, the general formula is the stronger the acid, the weaker its conjugate base, and the weaker the acid, the stronger its conjugate base. And here on the next slide, we can kind of see this. We're going to consider now HCl is definitely an acid. This is our famous strong acid. And we can consider Cl now as being a base, because that's what results when HCl, through the eyes of equilibrium, reacts. However, Cl is extremely weak. In fact, its basic property is negligible. So first, before we continue on, you can see that acid strength increases as we go up, and base strength increases as we go down. So this is the weakest of the bases, Cl-. Then as we go down here, here is a weak acid, phosphoric acid. This is a quite weak acid. In fact, it's found in soft drinks as a flavoring agent, a flavoring enhancer. Its conjugate pair is a weak base. So this guy would be a weak base. So it does have basic properties, even though they are weak. And if you go down here, the weaker you are as an acid, the stronger you are as a base. So if you think about, say, this substance here, this is very weakly acidic, which means its conjugate base will be quite basic. And if you keep going down to a place where you find a substance that has negligible acidity, not acidic at all, its conjugate will be very strong as a base. And notice in both cases here, water is kind of the defining substance, down here and down here, and all this, both of these surround water. So this is just a rehashing of the previous slide of what we said. Before we finish this lesson, let's talk about water in a little more detail, because water is so central to this definition of acids and bases. We said earlier that water is amphiprotic, which means it can act as both an acid and a base. And whenever you have pure water, if you have a glass of absolutely pure water, it turns out that in that glass you have the two water molecules interacting with each other. One acting as an acid, the other acting as a base. So this, in this case, actually, it looks like this water molecule is giving up the H+ to the other one. And you end up with a conjugate acid and a conjugate base. And this is referred to as autoionization. It's strange, but this is what happens in water. Now this happens to a very tiny extent, and we'll see in a minute how small the equilibrium is. Most of the water molecules actually lie on the left side. There's a very small amount of these that actually form. And we can write this out then as an equilibrium constant, and the equilibrium constant would give us Kc equals H3O plus multiplied by OH minus, because recall that your two water molecules on the left side were liquids, and those did not go into the equilibrium expression. So on the left side, here's what we saw. And because liquids do not go into the equilibrium expression, all we have are the products. And that's why we call this the ion product constant for water. It has a special designation. Its equilibrium constant has a special designation, and that is Kw. And Kw's value is 1.0 times 10 to the negative 14. A very important number that we will actually keep using over and over in this and the subsequent chapters. So, if you solve for either H3O plus or OH minus using this equilibrium constant, you'll see that the concentration in pure water of both of these is 1.0 times 10 to the negative 7. And the way you would solve this essentially is if you plug into here, into this first equation, not plug, but if you rearrange the first equation to solve for either one, because we know what Kw is, then we can square root that and get the concentration of H3O plus and OH minus. If this is a bit confusing, it'll clear up, I think, on the next slide when we do this example. So here we're asking to calculate the concentration of H plus in the following solutions. So in A we have a solution that has a hydroxide concentration of 0.010, and we're going to use our Kw expression. So Kw, we said, was 1.0 times 10 to the negative 14, which, if we write it out, is OH minus times H plus. Now I realize that I'm actually writing H plus instead of H3O plus, and H3O plus, this is the hydronium ion, is exactly the same as H plus. So sometimes, for brevity, we ignore the water. We take the water out and we write H plus, but these are exactly the same. So what we want to do then is rearrange the equation to solve for H plus, which means we're going to divide hydroxide ion concentration. Oops, this actually, I miswrote this. This should be a minus, not a plus. So what we'll do is let's go ahead and bring the OH minus to the other side, and we get ourselves an equation that looks like this. 1.0 times 10 to the negative 14 divided by OH minus concentration, which in this case is 0.010, equals our H plus concentration. So if we divide this, try to do this in your calculator real quick, and you should get yourself an H plus concentration of 1.0 times 10 to the negative 12th. And this is the answer. So what we see here is in water, in pure water, the more hydroxide ion concentration you have, the less hydrogen ion concentration you have, and that will always be the case. Notice the amount of H plus is really, really small. This is a tiny number, a trillionth or so of molar concentration. The second part B does exactly the same thing, except with a more varied concentration of OH minus. So why don't we just plug and chug again? Your Kw, which is 1.0 times 10 to the negative 14th, again equals your H plus concentration times your OH minus concentrations. So let's go ahead and solve for H plus again. And H plus is simply 1.0 10 to the negative 14, again divided by OH minus, which is 1.8 times 10 to the negative 9, which gives you, go and plug this into your calculator, using scientific notation. We should get 5.6 with two significant figures, 5.6 times 10 to the negative 6th as our concentration of H plus. and this is molar, so we should really put molarity behind it, and so is this. Both of these are calculated in terms of molarity. And here's a little clarification. It says in most of these KW calculation problems we'll assume the temperature to be 25, because recall, temperature does affect the equilibrium constant. And that should conclude Lesson 1 of Chapter 16.